So let's do a standing wave resonance example. Let's say we have a long tube with one end open and one end closed. And we're looking at sound waves in it. And we want to know, how long does the tube have to be to have a fundamental frequency of 150 hertz? I'm saying for sound waves. I may not put that in an actual problem because those are the only kinds of waves that we have traveling in long hollow tubes. So how long does it have to be to get this fundamental frequency? And then I guess part B is what is the frequency of the next harmonic? And even though it doesn't ask for this, I strongly recommend drawing pictures of the standing wave pattern to see what's going on for this. Okay. So the waves we're looking at here are sound waves, and we're not told a temperature. Remember, our sound velocity equation has a temperature in it. So if we're not told a temperature, assume the value at room temperature, which is 340 meters per second. I probably wouldn't mark down if you used 340 something, if you actually plugged a number into the equation we learned, but you are allowed to just use 340 if it doesn't tell you a temperature to use or something like that. So this is the velocity we're going to use for our waves. Sound problems are nice because we almost always we know this to start with. So we know that we want our frequency to be 150 hertz. And we also know that this is the fundamental. So I guess I'll write that. And we know for one end open and one end closed, we know what the fundamental looks like. Right, it looks like this. And if we remember our equation for that, we know that lambda was equal to 4L. So we want L. So to figure that out, we need lambda. But luckily, we know our frequency and the velocity. So V equals F lambda, or in other words, lambda equals V over F, which is equal to 340 over 150. So meters per second divided by hertz gives us meters, and 340 divided by 150 is 2.27 meters. So we know our wavelength, 2.27 meters, or that's, 7 feet or something. And we know lambda is equal to 4 times L, so L is equal to lambda over 4. That is 2.27 over 4, which is equal to 0.57 meters, or that's roughly, 2 feet or something like that. So a tube this long with one end open and one end closed is going to give us a fundamental frequency of 150 hertz. And that is the end of the first part of the problem. The second part is, what is the frequency of the next harmonic? So the next harmonic is going to look like this. And again, it's good to be able to draw these from scratch in case you need to. So it looks like this. We also have an equation for this. I mean, we could figure it out based on the distance between the nodes, but we also could just write down lambda is equal to 4L over 3. And L here hasn't changed, right? So our L is still 0.57 meters. So sorry, lambda is equal to 4L over 3, which is 4 times 0.57 over 3. So that is 0.756 meters. So that is, significantly shorter than this wavelength. And if we then plug this into our we'll work over here. If we plug, so this is our lambda. If we plug this into our v equals f lambda equation to solve for f equals v over lambda, which is 340 over 0.756. That is equal to 450 hertz. End of problem. There was another way to get to this, and that is you can see if lambda goes down by a factor of 3, as it does from here to here, we know that our frequency also has to go up by a factor of 3, right? Because v equals f lambda, and v is not changing. V is just 340, it's constant. So if lambda goes down by a factor of 3, v has to get bigger by a factor of 3, so 150 hertz times 3 is 450 hertz. So that was a shortcut if we wanted to take it. That certainly is acceptable. All right, great. So just in the interest of curiosity, how would this problem change if instead of asking about a system where where one end was closed and one end was open, how would it change if we had both ends of our tube open? And I'll leave these numbers up. So what if we had a tube that looked like this and we wanted to know the same things? How long does it have to be to have a fundamental frequency of 150 hertz? So what happens? So our picture is different. For this one, lambda is equal to 2L because this length L is equal to half a wavelength, lambda over 2. So in that case, our frequency is still 150 hertz, right? This is what we're trying to find. And that means our wavelength, v is still 340, f is still 150, so lambda is still the same. It's still 2.27 meters. And so L, instead of being equal to a quarter of that, L is equal to half that. So now L is equal to 2.27 over 2, which is 1.13 meters for this case. So these two, remember, these two are for the one end open, one end closed tube. So here we have a longer tube that gives us that same 150 hertz frequency. And now the next wavelength, remember if we draw the standing wave pattern, it looks like this. And our equation for that was lambda is just equal to L. So that is just equal to 1.13 meters. And if we plug that into our equation, so F equals V over lambda, so that is 340 over 1.13, we get 300 hertz, which we also should have known because if we make the wavelength shorter by a factor of 2, we make the frequency bigger by a factor of 2. So even though both of these tubes, both of these instruments, if you will, have the same fundamental frequency, they have different sizes and they have different next harmonics. They have different harmonics.